So now we prove Mashke's theorem. So let G be a finite group and V is a representation over some field K of characteristic 0. And suppose we have a sub-representation W of V. So then there exists a sub-representation U of V complementary to W, which gives us V, this is iso to this direct sum. So this is the theorem we want to prove. So first thing is we will try to use linear algebra and see how far we can go with that. So you start with some projection map, and this projection map say is going from some space, direct sum like this, and projects to a W. So you're going from V to W. So all these elements U are getting mapped to 0. So this projection map is onto this W, and this is a K linear map. So that is V is equal to U plus V, then pi of V is just W. So this map in fact gives us a complementary vector space to W. So you can set kernel of pi as U, then V is kernel of pi plus U. So because this space is complementary, so kernel of pi is actually a complementary space. So with this you can see by this. So pictorially you're going from V, this is your space W, this W gets mapped to W, and this goes to the kernel. So this is the complementary space. So this is your projection map. So we can prove this also. So kernel of pi is a vector space complement. So because if V lies in the intersection of kernel of pi and W, then V has to be 0. Because W is getting mapped to W. For W nothing is changing, you're just recovering all of W. Second is that if you apply pi to V minus pi of V, so V minus pi of V means that everything which is outside W, so everything which is outside W will lie in V minus pi of V, because pi of V gives you elements W. So if you apply pi to it, then this becomes 0. So that is anything which is complementary to W lies in the kernel of pi, because this is the complement to W. You apply pi to it, you will get 0, and that we can see. You can write it this as pi of V, and then projection composed with projection. If you compose projection with itself, once you have landed in W, you write projection map again, you still get W. So this is again still projection map. So you get pi V minus pi V, which will give you 0. So you do get a complementary vector space. So kernel of pi immediately gives you the complementary vector space. But now the problem is that we have to show that we need some kind of a sub-representation. So not a complementary vector space, but a complementary sub-representation. So that is more problematic. So for sub-representation, you know that sub-representation is basically G invariance. So we have to show this G invariance, and therefore we will have to modify our projection map. So we will modify our projection map pi to some new map pi prime, and this pi prime will again go from V to W, and it will satisfy the following properties. So first, pi prime of V would be an element of W. So this map should make sense, and then pi prime of W should be W. So these two will make this pi prime into a projection map. So it will satisfy the same properties as pi, as any projection map would do. So you will have that pi of V is W, so this is pi prime of V is W, and then W is just W. So this makes pi prime into a projection map. So we have to still define it. So you have to still define this. Then we will show that pi prime is G linear. So once we show pi prime is G linear, then kernel of pi prime is G invariant. So this 3 will then show that kernel of pi prime is G invariant. So once it's a G invariant, then you have a sub-representation. So again, first two will imply that pi prime is a projection, because you need a projection. Once you have a projection, then you can construct a complementary space like this, and once you have a complementary space, then we have to show this complementary space is G invariant. So this fourth will be implied by third, and then we will get this direct sum. So we already have this from the projection, but what we need is a direct sum, and for this we need G invariance. So let us start by first defining what is pi prime. So pi prime, you can say some kind of an average of projection. So pi prime of V we define like this: 1 over this, whatever elements there are in G, whatever the number there is, number of elements here, then you have apply rho of G here and rho of G inverse here, and this is your vector V. So now we have to check all these 4 properties so that our theorem holds. So now we want to first prove this number 1 here. So we are saying this should lie in W. So notice this map. So you first have this rho G inverse. So rho G inverse obviously will go from vector space V to V. Then you have the projection map which ends up in W, and then you have this rho G of map. So rho G acts on W will still give you W, because W is already a sub-representation. That is what we are assuming. Suppose we have a sub-representation W, that means it is already G invariant, so this holds. So now you first applied rho G inverse, then you applied projection, landed up in W, then you applied rho of G, landed up in W. So this does land up in W, so the first holds. You can also notice that pi prime is actually k-linear, because it's a combination of all these maps are k-linear. So projection map is obviously k-linear, and these 2 maps are k-linear because our vector space itself is over field K, and this rho of G is a matrix, so therefore k-linearity holds. Now we show number 2. So for number 2, again just copy down the formula here. This we are copying down right here. So now start thinking about it. So W is already G invariant because it's a sub-representation. So that is the definition of sub-representation. So this is G invariant. So this is going to be some element of capital W. The element could change, but still lies in capital W. And the projection map, this always takes W to W. So that is the definition of the projection map. So if V is like U plus W, then the projection map will take this W to this W. So projection map does not do anything to this because this is already in W, so projection map is not going to change it. So this is our original projection map pi. So therefore this just comes right here. So now you have rho G inverse, but now you can combine these 2 elements, which will give you the identity, and now you can sum up over all W, and this will just give you this W. So 2 is done. So for pi prime to be G linear, we have to show this thing, so this commutativity. So rho of H composed with pi prime is same as pi prime composed with rho of H. So you start with this side here. So for pi prime you have this formula here. So once you put rho of H, this will go inside. So we have copied this entire thing here with rho of H coming from here inside by linearity. So it is inside now. So when it is inside, you can combine these 2 to get this. This pi is here, and this G inverse is here, and this we add H inverse H to it because this is just 1, so nothing has changed. So from here you have just gone to here. So again this you copy as such, pi is as such. Now instead of G inverse H inverse, you can write it as HG inverse here, and this H you transfer to here. So this row comes with this H here, and this V is here. Now instead of HG you write G prime and do change of variable. So instead of going over G, you can do G prime. So this thing becomes this. So this becomes G prime, and everything. So this is the same as this, as you can see. Instead of G we are writing G prime. The only difference is instead of V we now have this rho HP. So this is just change of variable here. Instead of G you have G prime, but instead of V we have rho H of V. So this is again our definition of pi prime. So we have pi prime instead of V, now we have rho HV. That's what we write. and that is precisely what is on this side and we had to prove. So we have shown that pi prime is G linear. So now we use this G linearity, that is number 3, to prove this number 4, that kernel of pi prime is G invariant. So this is what we have to show. Rho of G of kernel of pi prime lies within kernel of pi prime, or more precisely, if V lies within kernel of pi prime, then we have to, and say H is an element of G, then we have to show that rho H acting on this V lies in kernel of pi prime, which essentially means we have to show that this pi prime acting on this rho H of V is 0. So this is what we have to show for G invariance of the kernel of pi prime. So this is just the definition. So let us start it. So first you have this rho of H acting on pi prime of V is 0, precisely because pi prime of V is 0, because V lies in the kernel of pi prime. And now this is equal to this, the commutativity, essentially, which we proved here. So this is what we proved here. This you're copying here, and now this is 0 here, because rho of H acting on 0 will give you 0. So this is also 0, and this is what we wanted to show. And that ends the proof of the Mashke's theorem.